Before viewing this video, make sure that you've looked at the Desmos application and make sure that you're able to plot the vector fields, or excuse me, the direction fields using Desmos, because part of that is part of these types of problems is being able to use Desmos to be able to verify your answer. So I'm going to give you three first-order differentials. And what we're going to do is we're going to plot the direction field using a computer algebra system. We're also going to find the equilibrium points analytically, and then we're going to trace those equilibrium points. This is actually a really easy type of problem. Sometimes those are called stability points as well. So if you've ever heard that phrase before, equilibrium, stability point is the same. So all we're going to do is we're going to start by setting the derivative equal to 0. It's almost like the critical values from calculus 1. So we get 0 equals 2 minus y, and that's the same thing as saying y equals 2. Now, I plotted the slope field, and I'm going to go ahead and incorporate that into what we have here. So just bear with me one moment. All right, and there's our slope field. And let's go ahead and take a look at what happens to the graph of the slope field at y equals 2. Right? So here's y equals 2 right here. And I want you to notice that all the slopes are equal to 0. And that's our stability point, our equilibrium points on the slope field. So that's how easy it is to find an equilibrium point, which means that the change, or the rate of change, is not going to be equal to anything at that point. Now, it's not necessarily always going to be a linear relationship, okay? Sometimes it's a different type of relationship. So a second example of this, we have dy dx equals x minus y. So we're going to set this derivative equal to 0, or in other words, y equals x. So this is going to be the family of functions for where the slope is going to be equal to 0. And we know what y equals x looks like. Y equals x looks like this, approximately on the graph. All right. Let me go ahead and incorporate that graph into this image. Okay, so I went into Desmos, plotted the graph. Here's our graph. And let's take a look at the line y equals x. All right, and you have to be really careful because it passes right through the origin. But if I plot that point, or if I plot that line as best as I can, then we end up with this relationship. And I want you to notice that every single slope that falls on that line exactly is 0. So if I was to randomly pick a slope, well, there's a slope, it's 0. All right. If I were to randomly pick another slope, maybe like really close to the origin, right there, that one's 0, this one's 0, this one's 0, etc. All right, so that's what an equilibrium point is, okay, and that's the series of equilibrium points. Right? Not necessarily for every differential is there only one family of equilibrium points. Okay, so a third example of this. Right? So we have this pretty nasty first order, where we have dy dx plus 2y equals 2y cubed minus 3y squared. All right, so we're going to have to do a little bit of solving for this. All right, so let's go ahead and solve it. First of all, we're going to set it such that dy dx is going to be equal to 2y cubed minus 3y squared plus, or minus 2y, excuse me. We're going to factor this out. Okay, so dy dx, we're going to factor a y out of it, and we're going to be left with y squared minus 3y minus 2, or 2y squared, excuse me. And then finally we can factor that trinomial one more time, and we get that dy dx is going to be equal to y times 2y plus 1, y minus 2. All right. And what that does is that gives us three lines that are equilibrium points. So the first one is going to produce y equals 0. The second one is going to produce y equals minus 1/2. And the third one is going to produce y equals 2. So these are the three lines on the slope field that should produce equilibrium points. Right? So let's go ahead. I plotted it in Desmos, and we're going to go ahead and see if indeed that makes sense to us. So let me go back over here. I'm going to plot this. All right. I am going to get rid of this stuff down here. We already know the 3 lines. I'll write them in again once I erase all this. This is just for convenience for the next series of stuff. And so let's look at those 3 lines again. Okay, so remember we had the lines y equals 0, y equal 2, y equal minus 1/2. Right? So at y equals 0, even though we can't see it too well, there most certainly is. Right? If you zoomed in fact, if you graph it on your own, you could probably see that there's like these lavender or purple. Sorry, I'm not an artiste. All right, but those are the slopes, and they're kind of buried in that axis. We have y equals 2. That one's really obvious. And unfortunately, the graph doesn't capture the 1/2. So you might have to zoom in. All right, but there is a line on there, and I'm going to have to erase these. But there is a line, we just can't see it at 1/2. So if I was to go ahead and trace it, in fact, I'm going to zoom in. All right. And probably, and this is not going to be too good, but probably right here through this line, right, you're going to have this sort of stuff going on. So you'll probably have like one of these sorts of relationships. Right? Now, Desmos didn't capture it. Okay, can't capture everything, and that's one of the benefits of having the analytic solution in tandem with the geometric solution. All right, as you know from Calculus 1, Calculus 2, Calculus 3, whatever you've taken math before, the graphing calculator doesn't capture everything. So that's why we need these algebraic, also known as analytic solutions. Right? Another thing that we can look at with respect to slope fields are these isoclines. All right, so shifting topics, just as a reminder what an isocline is. An isocline is similar to an equilibrium point, except that the slope is the same on all, is just the same. Okay, so it might not necessarily be 0, but the slope is the same on all of on that curve. All right, so it could be a quadratic, it could be linear, it could be cubic, it could be sinusoidal, it doesn't matter. All right, so what we're going to do is we're going to find the family of isoclines, and then all we're going to do is we're just going to trace several of these on the graph or in the computer algebra system from Desmos to see if indeed that's true. All right, so a really easy example of this. So what we're going to do is we're going to say that C equals negative y, or in other words, y is equal to minus C. All right, so this is the family of isoclines for that differential. What is that? Well, that's just a bunch of horizontal lines. And let's take a look at the graph, and we're just going to plot a bunch of horizontal lines, and we're going to see whether or not it makes sense. All right, so let me go over. So bear with me one moment while I copy this. Right? So let's just draw a horizontal line, okay, anywhere on the graph. So I'll just pick y equals 3. So here's a horizontal line through y equals 3, and I want you to notice that through every single one of those, that the slope is negative and the slope is the same at that point. Okay, another one. So let's go ahead. I'll go through negative 5 just because I can. So right here. I didn't mean to pick almost the same color either. Like I said, I'm not an artiste. But right here, clearly, all the slopes are greater than 0 and all the slopes are equal to one another. And I could do this as many times as I wanted. In fact, if I went to pretty close to the origin, I'll go right here. And that's what an isocline is. All right. Again, an isocline means that all the slopes are the same on those lines or curves. All right. Doesn't matter what the slope is. It doesn't have to be 0. So essentially, equilibrium points are a subset of isoclines. All right. A second example that's not necessarily linear. So this time we have dy dx equals x squared plus y squared. Right? If I go through and just set that equal to c, so we have c equals x squared plus y squared, and what is that family? Well, we know that that's going to be a family of circles. Okay, so this is circle. The center is at the origin, 0, 0, and although it doesn't really matter, the radius is a variable, and the radius is the square root of c. So essentially, every circle that we draw centered at the origin should have the same slope as we go through and plot that on the curve or on the circle. So let's verify that. So, and I hope what you're doing is you're also plotting these along in Desmos to get practice. All right. If you're not, make sure at the end of this video to go back and plot these just to make sure that what you have is correct, that you do know how to use the Desmos app. All right. And I'm going to zoom in just a little bit for this one. And let me go ahead and draw a circle of radius 4, just because I can. Or I'm going to try my best to draw a circle of radius 4. It's probably not going to be all that good. It'll probably end up being more elliptical than circular. All right. And so I know it's not exact, but I want you to notice that if I was to pick randomly some points, let's say right here, that's a point on the circle. If I went right here, this should have been a point on the circle. This is a point on the circle. This is a point on the circle. This is a point that should have been on the circle. All right, I'm just limited by what I have available to me. It's very obvious that all of those slopes are exactly the same, hence it's an isocline. A second example, let me go ahead and craft the unit circle on this graph. All right, so if I craft the unit circle, I'll draw that one in black, radius 1. All right, so get this guy right here. It's probably not that good. Let me try to redo it. All right, and again, we look at all the slopes, and all the slopes are approximately 2 at that point. All right, since 1 squared plus 1 squared is 2. All right, so that's what an isocline is. One final example. Let me give you a quadratic example of this. So we have this dy dx minus y is equal to x squared. So we're going to say c is equal to c minus y is equal to x squared. We could subtract c from both sides. So we get negative y equals x squared minus c, and y equals c minus x squared would be the family. All right. Now we know this to be the series of concave down parabolas at the point 0c with the vertex. Okay, so we can say concave down parabolas. The vertex of the parabola, if I substitute 0 back in for x, we're only left with c. So the vertex of this, or at least a point, would be 0c. All right, and we know that as we shift it up and down, all right, we know that it just keeps getting smaller as x gets bigger no matter what. So truly the maximum is at the point 0c. If you don't believe me, go ahead and use the formula minus b over 2a. You'll see that it does work. All right, so finally what we're going to do is we're going to plot this on the vector, on the slope field. All right, so let me just go ahead and incorporate this. And let's just plot a few of these concave down parabolas just to verify. All right, so that's our slope field. Again, I'm going to zoom in just a little bit to get a better picture of this. Desmos is really resolute. Resolution is very high. Let's just draw one at the origin. All right, so I'm going to do my best to draw this concave down parabola from the origin. All right, and I'm just going to pick a few random points. So here's one, here's one, here's one, here's one, here's one. And we know that all the slopes are going to be equal to 0 that fall on that curve, which makes sense because It's just going to go x and c are going to be the same values as we go along with this. All right. One other example is, let's just shift it up 6 units and draw the exact same thing. All right, so I'm here, and I'm just drawing something like this, the same parabola, as best as I can. I know it's not all that great. This one should have been over a little bit more. But if I was to randomly pick some points here, all right, they all look like they have a very steep but positive slope. Right? So that family of concave down parabolas certainly represents the isocline for this. Okay? So hopefully that gives you a good idea as to what an isocline is, how to find them both analytically and geometrically, and use that Desmos app. Okay, it's very helpful and also very accurate as opposed to graphing by hand.